Dots.
Okay.
Yeah,
thank you very much. So thank you all for coming along to listening to this webinar on some of the acoustics and audio work that we're up to at BCU. So my name's Ben West. I'm a lecturer in audio engineering at BCU, and I'm going to give you quite a quick, fast 15-minute summary on one of our projects, which is looking into office soundscape assessment methodologies. And this project has been running for about 12 to 18 months in collaboration with Arup, particularly the Birmingham office. And I'm going to kind of talk through pretty standard set of slides, pretty much from a background through to conclusions and further work for this project. Okay, so in terms of background, why were we completing this work, basically? Sound in offices is important. Acoustics in offices is important. There's quite a lot of work that shows that. There's been work that shows that office acoustics or sound noise in offices is related with job satisfaction, productivity, and also overall well-being. And because we're acousticians and we love a standard, there are a couple of standards that detail objective methodologies for assessing office acoustics, office sound. So we've got ISO 3382-3 that kind of details objective parameters like reverberation time, and then 22955, which details other objective parameters we can measure in office environments. If we're interested in the subjective impression of office acoustics, it's a little bit less clear what methodologies we should use to assess office acoustics or office soundscapes. ISO 22955 gives us an example user survey, which is quite a long survey actually, and it doesn't give any analysis procedures. So if you were to complete that survey in say a client's office, then it might not be so clear how to analyze the data. And then if you look at research literature, there are many different types of subjective methodologies that have been suggested over the years, which all are great and have various different applications, but it would be difficult to know which particular subjective methodology to use for a general assessment. So where we came from with this work, where we were arriving at this, was that we're all kind of quite interested in the soundscape approach, and this has been gaining traction, particularly in exterior environments. So it's a very perceptual oriented method of assessments of acoustic environments. And ISO 12913 series now defines soundscape as a word and also details this two-dimensional model for soundscape assessment. So in other words, you ask occupants of a space, as I say, 12913 is for exterior spaces. You ask occupants to assess the space using these 8 words, and then from these 8 words, calculate a two-dimensional kind of score or perceptual position along this pleasantness and eventfulness dimensions. So we thought, well, that sounds quite useful. That's being used more and more in exterior environments. Perhaps it'll be useful in office environments. The kind of complication is that this was developed for exterior environments, and recent work by Torrison and others at UCL has developed a similar but slightly different two-dimensional model for residential environments. And qualitative work into office soundscapes has suggested other words or other important factors for office soundscape perception. So even if we want to apply a soundscape approach, it's not ever immediately clear which kind of approach to adopt in office environments. So the aim of our study was to, first of all, understand whether or not office soundscape assessments are appropriate in office environments. And if so, what assessment methodology we should use, what kind of words should we be asking people to assess the offices that they work in using. Okay, so what did we do? We completed what I'll call office soundscape assessments in a number of different floor plates, and that included kind of 2 types of methodology. So one was a questionnaire that we sent out to all occupants of the office on each test day. And the other part was objective measurements, and I'll talk about that in a minute. But in terms of the questionnaire, we asked the participants or the occupants of the real office that they were working in, this was all in situ, to assess the acoustic environment, the soundscape around them using 26 unidirectional attributes. So we took 8 words from the ISO 12913 standard, 8 words from the Torrison residential study, 8 words from the qualitative soundscape office soundscape study that I mentioned before, and then a couple of extra words that came from translations that have been used in office environments. We also asked the participants to assess the soundscape overall. So this is the overall good or badness of the soundscape, and also the soundscape appropriateness. So they're two questions that are straight from ISO 12932. We also asked participants to assess the presence of 4 classes of sound source. Again, this is something that ISO 12913 asks you to do in exterior environments, and we tweaked the classes to be appropriate to office environments. So, for example, we replaced I think it's construction or traffic noise one with mechanical and electronic sound. So those classes were more appropriate to the office environment. We also collected some contextual data in the questionnaire. So we asked participants to assess their overall work-related quality using 3 metrics that were used in other office soundscape studies. So satisfaction, willingness to work, perceived productivity. We asked participants to rate their overall well-being using the World Health Organization 5 index, which has seen success in other soundscape studies. And we also asked participants to self-report the tasks that they were up to in the office, whether or not they consider themselves to be orally diverse, and also gender. If we have time, then in the questions we can look at the results for those categories, but I don't think we'll have time in the original 15 minutes. In terms of the objective data that we collected, so the workstation noise level measurements were completed in accordance with ISO 22955 on every test day. So while the participants, the occupants in the office were completing the questionnaire, we were also collecting workstation noise levels using sound level meters. So we positioned the sound level meter in every kind of acoustically different zone in the office. So in other words, if we had a big floor plate like this with 4 distinct zones, corners, teams working in these zones, then we would position a sound level meter in each zone within the office. We assessed 8 floor plates in total. We repeated the first one because the occupancy in that floor plate was low, and we wanted to increase the survey numbers in that floor plate. And you can see that we collected a range of floor plate areas, ceiling heights, overall capacity, occupancy on the day, and also overall sound level. So we've got a range of about 8 decibels between the sort of lowest level and the highest level in our data set. Okay, so very quickly move on to some results. I'm going to talk through some principal component analysis results first. This has been used in the exterior and other interior soundscape studies that I mentioned before. So PCA is really useful to help us reduce a large number of variables down to a smaller number of variables. So in our case, we use this to try and look to see whether or not rather than ask participants to assess the soundscape against those 26 original words, whether or not we could have asked them to assess against a smaller subset of factors or components or words. So we found that the first 3 components explained almost 60% of the total variance in this variable data set. And if we plot the components against each other, we can start to see which variables load on each component, and from that, which component explains behavior of various variables. So if we look along the x-axis, on which we plotted component 1, we can see that in the positive direction, component 1 was best explained by comfortable, pleasant, promoting concentration. And then in the negative direction, best explained by demotivating, irritable, disturbing, annoying. So we labeled that component pleasantness, and it's quite common to label the principal components once you found them. The second component, plotted in the y direction, best explained positively by eventful and negatively by uneventful. And unsurprisingly, we labeled that eventfulness. And again, you've probably guessed what's coming next, that we feel that this compares quite well with the ISO 12913 suggested 2-dimensional model. well, first of all, we've plotted the component one along the X direction and eventfulness along the Y direction. But you see, for example, variables with positive loadings for both pleasantness, component one, and eventfulness, component two, are similar to things like vibrant, engaging, interesting, which is in agreement with the ISO 12913 two-dimensional model. And we see a similar behavior for example, calm, boring, monotonous, and then chaotic. So in other words, we think that this gives us reasonable evidence to suggest that the ISO 12913 two-dimensional model is useful for assessing open plan office soundscapes. Okay, what's also interesting to look at, if we then calculate those two-dimensional eventfulness and pleasantness scores, is to then look at how they relate with the other variables that we collected in the study. So to look through some of the kind of interesting findings from that, sounds from human beings, so this is the participant rating of the presence of sounds from human beings, was positively correlated with eventfulness. So in other words, the more sound from human beings people can hear in the office, the more eventful they perceive the soundscape to be, which is agrees with findings from exterior soundscape studies. But conversely, sound from human beings was shown to negatively contribute to soundscape pleasantness. So when designing an office, a floor plate for its soundscape, there's probably a balance between how much sound from human beings you want to introduce or design into the space to create an eventful environment, but without leading to an unpleasant environment or an annoying environment because there's too much. Similarly, mechanical and electronic sounds were shown to negatively contribute to ISO pleasantness too, which again probably isn't groundbreaking to the consultants out there, but it's nice to show that this soundscape method is bringing out these things that perhaps we thought we knew anyway. And also office soundscape pleasantness was positively correlated with those work-related quality questions, so work-related satisfaction, willingness to work, perceived productivity, and also overall psychological well-being. So there is an argument that psychological well-being possibly underpins how we feel about satisfaction at work and willingness to work, and then also our perception of the soundscape. But other studies have shown that office acoustics and noise in offices is directly related, has a causal relationship with psychological well-being. So we're obviously not proving that kind of causal relationship between soundscape perception and psychological well-being in offices, but I don't think we should necessarily reject that at this point, and it's worth investigating further. And of interest for the consultants in the audience, we showed no correlation between any of the level-based indicators that we calculated from the sound level meter measurements and our perceptual scores. So there was nothing that we could measure on the day with the sound level meter that was useful for then predicting office soundscape perceptual performance. It is worth noting that we could only measure level-based indicators because we weren't given permission to record audio in the offices. It's always a problem with in situ office acoustic measurements that the occupants are not very happy with you recording their conversations. So that's something we need to look into in further work. Okay, so brings me nicely onto conclusions and further work. So kind of key three conclusions. We think that the similarities we've identified between our main principal components and the ISO 12913 two-dimensional model suggests that model is applicable to open plan office soundscape assessments. And if you have maybe subjective issues in an office, or you're looking to assess an old office to then design a new one for those occupants, this method should be useful. We found that sound from human beings was negatively correlated with ISO pleasantness, but positively correlated with eventfulness. So there's that trade-off there. And also that there's this relationship between psychological well-being and work-related quality and soundscape pleasantness. So just to touch on the further work that I mentioned, we plan to, this work so far, as I said, is useful because it gives an assessment methodology for office soundscapes or a perception of office acoustics. But what it doesn't do so far is, if you complete an office assessment, soundscape assessment using this method, it doesn't then tell you what to improve or change in your design to move to a different part of that perceptual space. So we plan to investigate that further. We're really fortunate to have installed recently a sound lab in partnership with Arup at BCU. So we plan to use that environment where privacy is not an issue, and we can record and manipulate, synthesize audio to investigate office design parameters further, and also room acoustic and psychoacoustic indicators for then predicting office soundscape performance in the design phase. Obviously, that's much easier where we can calculate any audio-based psychoacoustic indicator without any privacy issues in a virtual environment. Okay, I think I was pretty much just on 15 minutes there. Does anybody have any questions on this part of the presentation?
There's a question, there's a couple of questions in the Q&A. Can you see them?
No, I can't. I can stop sharing and have a look, but
okay, I can. So with
okay, great, thank you.
Occupancy varying greatly from space to space and day to day, how did you decide what occupancy level was appropriate for measurement?
Yeah, so that's a good question for this experiment, because what we were looking at was different assessment methodologies and trying to prove which assessment methodology to use. We wanted actually just a range of occupancies, so that's why we ensured there were some unusually quiet offices and then kind of the busiest, most occupied offices that we could find. For actual using this method in situ in practice to try and quantify the soundscape perception of an office, you would probably want it to be as representative of the office when in use, in normal use. But it's pretty difficult to determine what is normal use these days, post pandemic, with office occupancy varying quite a lot from day to day. But yeah, as far as this study was concerned, we just wanted a range, and I had a lot of days of measuring in very quiet offices due to various events like extreme weather events and rail strikes. So, but that's the woes of a consultant, isn't it, really?
Okay, thanks, Ben. Another question. Can you at least give an indication of how aurally divergent people responded?
Yes, definitely. So I will move to just an extra slide that I have in here. So yeah, we showed two significant relationships between both of the soundscape perceptual results, so ISO pleasantness and ISO eventfulness, between those with and those without an aural diversity. And I know that this is a pretty very broad brush analog approach to this and could definitely be improved, but we just wanted to make sure we captured something that acknowledged hearing differences. So those with self-reporting as being aurally diverse scored ISO pleasantness more negatively on average than those without. And similarly for ISO, well, not similarly, dissimilarly for ISO eventfulness, those with the self-reporting as aurally diverse scored the soundscapes more eventful than those without, which just further supports the rationale behind designing spaces for everyone inclusively and not just concentrating on the normal or typical listener, whatever that means.
Great, thank you. Another question. Does the soundscape approach lend itself to other room uses, e.g. hospital wards?
Yeah, so I think I would certainly say so. We're showing here that ISO 12913 is useful in offices. That doesn't necessarily mean that that method itself, that two-dimensional model, is directly useful in hospitals. But I think there's a good argument here that it could be. But overall, the soundscape approach should be useful. And that sounds like a really interesting project to work out whether or not in hospital environments, ISO 12913 is useful.
Okay, I'll just do one more and then we'll move on to the next talk.
Sure.
What sounds in sounds of human beings had the most negative correlations?
So we don't know that because we kept the questionnaire simple in accordance, well, similarly to ISO 12913. So it was a whole category of sound from human beings, and similar to ISO 12913, there was some suggestions. So it would have been speech, conversations, laughter, I think was the description. But yeah, it's a lumped in, grouped category.
Okay, Thank you.
Okay, thank you very much.
Thank you, Ben.
Hey, I'll just share my screen and yeah, so thanks very much, Ben, for that. I'm also from Birmingham City University. My name's Ali-MacLachlan, and I lead the audio and acoustic research group in Birmingham. I'm going to talk to you today about a project called Aural Histories, which we're 2 years into a 3-year project at the moment. My background is in sort of teaching of acoustics and generally within music technology, and I completed a PhD a few years ago on analysis of and classification of style in traditional Irish flute playing. So I guess that set me up a little bit to be involved in this project. Um, it's quite a large project in terms of the project team and the number of stakeholders. So I lead on the acoustics side of things, but we also have experts in early music and in historical architecture and performance and areas like that. So the idea behind it was to basically bring a team together to have a look at what happened in Coventry, particularly in the performance areas of churches between 1451 and 1642. So that's sort of from the Reformation to the English Civil War. Where the project should end up, hopefully in a year's time, is that we'll develop a set of VR models and digital tools to allow people to basically explore these sites, looking through history at what happened, and also being able to hear and experience those spaces. This is particularly important as the picture shows. St. Michael's in Coventry was bombed during the Second World War, so we've lost that as a space. And one of the things that we were keen to do was to imagine what that would have been like in various time slices with the kind of music that would have been played in there. So hopefully what I'll show you on this presentation is just some of the work that we've done, but also to pose some of the questions that we're sort of looking at the moment. So in terms of Coventry, this historical map shows the spaces that we looked at. The one which is over here on the left is St. John's Bablake. We haven't done any models of or acoustic models of St. John's Bablake yet, but I did go in and do some reverberation testing and frequency response on it. So in particular, the spaces that we're interested in were Holy Trinity, which is the space on the left of the cluster of three, St. Michael's, which is the large one, and also St. Mary's Guildhall, which is just opposite. So they're nice and close to each other. So the work that we've done so far is, as I mentioned, we've taken acoustic measurements of the venues using Room EQ Wizard. We've made models of Holy Trinity and St. Mary's Guildhall in SketchUp. We just have quite a new model of St. Michael's as well, which we're just starting to do some testing on. There was a lot of work done in research of period appropriate music, which was generally done by Professor Jamie Savan, who's the PI or the project lead on this, works for Royal Birmingham Conservatoire and is an authority on early music. So he was able to put together a sort of wish list of instruments and musicians that were able to play the kind of music that was appropriate here, and to record that. And the recording was done by Simon Hall, also from the Conservatoire, who's a great background in that type of recording. Sonification was created in Odeon, and we also looked at reverberation times for venues and started to compare models. Obviously, this is work that's in progress at the moment. So in terms of this flowchart, the two things that were going on at the same time were to end up with a set of recordings, which I'll talk about in a little bit more detail, because I think it's maybe important to think about how the recordings were collected and in what sort of way, and then also the CAD modeling to bring those two things together for sonification in Odeon. We're looking to play back in two ways. One is binaural. I will be able to play back some of this stuff, although I'm never 100% convinced that the audio engine in Zoom does it justice. But it certainly seems to be better than Teams, which I don't know whether Teams still works in mono or not, but it certainly did a while back. But as Ben mentioned earlier on, we also have our sound lab at Birmingham City University, so we're able to render out B format files generally in second order and play those back on that system. So they form part of the sort of general demo that we use for letting people have a listen to that. So if you're ever in the area and you want to have a quick listen, do let us know. So some sort of specific questions that we wanted to have a look at as part of this project. What was the effect of architectural changes? So I'll look at a couple of architectural changes through this, but you know, a good example of this would be this is a picture of St Mary's Guildhall on the right hand side. This is how it is now. But looking back through history, we can see that there was quite a large set of wood paneling that was in front of this wall that's shown at the end. It's also known as a rood screen. So that would have made some difference to the acoustics. Also, the minstrel's gallery, where music was played from, has gone through several changes with different tapestries and hangings. In fact, the tapestry which is in this room at the moment is sort of behind where the camera would be, and at the moment it's covered with a large piece of clear acrylic, which because of the size of it will have quite an impact on how it changes. So there'll be things like that we can have a look at. So what's the difference between reverberation times in models and also in existing venues? So to be able to take some data that we've captured from these and to verify the accuracy of models compared to real life, we felt was an important thing to be able to do. There doesn't seem to be very much data at the moment on those types of tapestries in terms of absorption coefficients. So we're pretty keen to do some work on that. And obviously we have to look at non-destructive testing in those sort of areas. So that's some work that we would like to complete. Also, what are the differences between directivity patterns of historical instruments and their modern counterparts? Again, a lot of the data that we tended to use in Odeon out of the box was for directivity patterns that are based on modern instruments. So I'll talk a little bit about that and the kinds of things that we could do. Also, can we record in any way other than anechoically? And is de-reverberation an option yet? Again, there are reasons why we want to look at those. So early in the project, we started by using Matterport to create LiDAR scans. And we did attempt to do some sonification as part of that. The quality of scans that we got from Matterport were great in that they were very quick to do, but we felt that it was very difficult to edit them and to try to model over the top of them to clean up lines to get crisp corners and things like that was very difficult. And in the end, I think we did what everyone else seems to do, and we moved to just using a sort of standard CAD models. So we use SketchUp because of the links between SketchUp and Odeon. We find this is very useful for what we needed. The model has more detail than we would normally need to do acoustic modeling, and that's really because the models are also being used for VR content as well. So, I mean, if anything, we could simplify those. Like, for instance, that spiral staircase wouldn't strictly be necessary in this, and it's probably not making that much of a difference. But in a way, for the amount of extra render time it takes, I'm quite glad to have details like that. At least we can say that we've got them. So if we look at Holy Trinity Church to start with, one of the things that the team was pretty keen to look at was that in 1630 there was what's called the Jesus Chapel. It was a raised chapel, so there was an area here, a gallery for the choir to be able to sing from, and there was also a raised area, a seating area on the other side of that. So in comparison with the 2023 version, these no longer exist. There was quite an extensive second floor in this church historically, and that was all taken out. So that would appear in the nave of the church, just on this sort of side. So we're interested to look at what sort of differences there would be in sound from those. So when I measured those, the model of Holy Trinity as it sits at the moment, it's an averaged EDT of 2.94 seconds. And you can see that the difference between that and historically isn't really a lot. There's around about 0.2 of a second there. But there is a bit of a difference when we move up into the gallery, where it's down a little bit. So I can let you hear what they would sound like. So here is Holy Trinity as it would be at the moment. Okay, here's what it would be like in 1630. And here's what it would be like from the first floor gallery. Okay, I'll talk a little bit about how these recordings and sonifications were done in a little minute, but I think sonically there isn't that much difference in there, and it'd probably be quite difficult to hear any differences. St Mary's Guildhall, again, we found that the addition of the rood screen didn't make that much difference. So in terms of overall reverberation time, there is about half a second of difference through various things, but one of the differences that we were interested in looking at is what's the difference in reverberation time from empty to full, because it's unlikely that historically performances would have been given to an empty room. So we were interested in looking at those. Okay, so that's it as it would be at the moment. And in the 1617 model, we have this. And if we put in an audience at 2 people per square meter, we would end up with this auralization. So we've yet to do large-scale listening testing on these, but that's certainly one of the plans that we've got using our facilities. So in terms of the recording methodologies, we started in each case with a recording of the ensemble, and then put individuals in an anechoic chamber in order to get individual stems. There are issues with doing this. Musicians don't always feel comfortable in this space. It's somewhere that they're not that used to. And also getting them to absolutely sync up with an ensemble recording can take some time. It's quite difficult. So other things that were tried, for example, were getting the ensemble in a recording studio where they had line of sight, but using dynamic mics. The reason behind using dynamic mics rather than condensers was to try to minimize the spill between them. We have another ongoing project on looking at changing frequency response differences between different mics. So we felt quite confident that we could then get back to the sound of a higher quality mic, or get back to some transparency. We also recorded the ensemble in venue so that we could try one recording against the other for listening tests. And as I mentioned, one of the things that we'll do with this for listening tests is playback through binaural or B format methods. In terms of directivity patterns, I'm particularly interested in having a look at directivity patterns of energy for historical instruments, particularly a cornet like this instrument. It's very different from anything that we could find in terms of directivity patterns. So I don't feel that the models were particularly be doing those justice at the moment. But also in terms of the sackbut, which is an early trombone, the bell is very different, and I've been told by players that it feels very different sonically to a trombone. So one of the side projects that we have at the moment is looking at what methods we can use to capture that data without basically using the very expensive way of just having a lot of microphones and a lot of space and creating that data. So we're looking at a few different methods at the moment, and we hope that would make a difference. The other thing that we'd be interested in looking at is de-reverberation. Now, I would say that de-reverberation at the moment is very much in its infancy. If I let you hear a trumpet call recording, and then I'll let you hear some de-reverberation that's done with Librosa, even on Zoom, you'll hopefully hear that there are quite a lot of artifacts. So here's the original. And here's the de-reverberation. Okay, so you can tell there's definitely less reverberation on there. Why would we do this? Well, certainly the feedback that we've had from the musicians is they would feel a lot more comfortable being in a recording studio. There are different ways to do this. I spoke to Brian Katz at a conference recently, who's done a lot of work in this area, and he tried getting a reverberation through a digital audio workstation of the live recording and putting that back through headphones. And he said that worked in some sort of way. But I don't think there's any way of getting around the fact that musicians feel less comfortable in an anechoic environment. So is a studio reverberation close enough? I don't think so, because it's different, and we really want perfection if we can get it. So so there is possibly a track to go down here, I think there may be a solution somewhere with machine learning trained on pairs of reverberation and dry recordings to try and get a little bit closer. But it's very much in its infancy at the moment, and it'd be a great project for someone to work on. So hopefully gives you an insight into the kind of work we've been doing on Aural Histories. At the moment, I'd be happy to take any questions. Thank you.
Thank you. There's no questions in the chat at the moment.
Okay,
But if there are any, you can answer them as we go.
that's great. Thank you.
Okay. Thank you. So Matteo,
Hello, that's me.
hi.
I'll
When
share
you're
my
ready.
screen.
Yeah, thank
Yeah.
you.
Hopefully you can see my screen.
Yeah, we can see that. Thank you.
Awesome. Hi all. I'm Matteo. I've been a PhD student and a lecturer recently at the same institution, BCU, the same institution as Izzy and Ben. And with this presentation, I wanted to give you an overview of projects alongside acoustics in augmented reality, which have targeted my PhD. So I'll be showing you PhD projects essentially and how I work towards the overarching goal, which is effectively to come up with a system that provides real-time rendering of spatial audio in augmented reality, which is a very difficult task because in augmented reality you have geometry that gets reconstructed as you look around with a headset. You have holograms, you have virtual entities, you have very dynamic conditions. And the goal is, can we even have some sort of real-time simulation of acoustics so that we can then oralize sources and that we experience holographically, so that we have like projected around us and we experience with the augmented reality headset. I come from a sound engineering background, but I've always sort of been at the intersection of different areas like elements of computer science or computer vision. So I've always liked this sort of cross-disciplinary research areas, which is why I chose this goal for my PhD. So as a high level, one of the applications that I envisioned at the time was, can we take a room like this, for instance, apply a bunch of modifications using an augmented reality headsets like the HoloLens and see if we can experience changes in the soundscape or if we can appreciate differences in perceiving sound in real time after having created our own sort of space that's a mix of physical space and augmented reality that's projected onto the space. So it was quite an ambitious research question, and we started tackling it from the problem of materials. So as you've probably seen the overview of the talk, this mostly focuses on recognizing and mapping materials from definitions of acoustic materials to environments that you can work with. So when working with a virtual environment, or typically in a game engine, as a lot of the work that I do is sort of viewed from the lens of games and games technology. So a lot of the experience I have is working in virtual environments and sound rendering using game engines. And one of the bottlenecks I found early on was the requirement of having to map materials to surfaces of the environment manually. So this was the first obstacle, because in a dynamic environment like augmented reality, you don't have the time to author and attribute acoustic properties to surfaces around you. And you ideally want some sort of automated system to do it for you, which is the first problem that we tackled. So given an environment and given a database of materials, if we, for a second, don't strive for realism or accurately matching the correct, for instance, acoustic absorption coefficients to the material that's represented virtually, and we just sort of focus on just creating some sort of system that maps visually a material to the best match from a given absorption coefficient database, for instance. So this was the first project, and we approached it using a convolution neural network, which essentially performs scene segmentation. So we had seen like a virtual environment and cameras within the virtual environment, and the goal was to have the virtual environment with acoustic materials attributed for every surface. So the way we did this is by performing scene segmentation using a neural network. So with each pixel being labeled as semantic label that the neural network recognizes, the system will then project this pixel back into the virtual environment using those semantics to map materials from an acoustic material database to the surface. This worked quite well, and was theoretically possible to have it operating in scene virtual environments if you train on a general enough database or dataset of renders and correctly assigned materials. But as we started working with LiDAR scans and newer technology to quickly obtain a virtual representation of a physical space, like a Matterport camera, or even the built-in LiDAR scanners in augmented reality devices, we started wondering if we could abstract away from the issue of having camera placements and having this sort of automated system that looks around and takes pictures effectively and then uses those to map materials. And we approached this by extracting textures from meshes and directly recognizing visual features on these textures. So having scanned the room, for instance, can we separate all objects into their own meshes and have a system that works on separate objects, extracting the texture and inferring the material based on visual features on these textures. So we did this by refining the neural network to abstract away from camera renders and look essentially just infer materials based on very small image batches. So we used a data set of surfaces, which is called open surfaces, which has photographs of surfaces in the wild. So for instance, marble, the semantic word marble will give you access to photographs of just marble under different lighting conditions, for instance, so that the network recognizes the material marble under different conditions. And this works better in the sense that it didn't require cameras, and you could just, for instance, have this mesh of this is a recital hall, and you could quite clearly see that the textures would express the sort of wood patterns of wood, and the network would effectively recognize these with decent accuracy. So this was the sort of first project issues that we tackled in terms of research. But the full pipeline should have a sound rendering component. So that works in conjunction with material recognition, because obviously with just materials you don't you need some sort of system that performs sound propagation. And initially we used off-the-shelf sound propagation, because why would you reinvent the wheel if we already have very good, state of the art out there? But in the long run, we found, and I found that it was quite difficult for me to integrate the component of material recognition to sound rendering without actually knowing what happens behind the scenes. So there was only so much we could go by treating it as a black box and feeding it materials and seeing information and having it performing sound rendering. And also the dynamic aspect of augmented reality and the fact that it's a wearable computing imposed a lot of limitations on the sound rendering system that you could choose. So we started dipping our toes on simple geometrical acoustics, because it's the sort of standard and this more simplistic system that you can use to propagate audio, propagate sound in a virtual environment, and started understanding how these systems work so that I could then better integrate material recognition into sound rendering. So we started very simplistically with the image source technique, which is now ancient history pretty much in the BC world of sound propagation research. But by comparing sound propagation in a virtual representation of a physical space and performing some comparisons with ground truth, we started noticing that actually geometrical acoustic can approximate reverb more or less. And we're not striving for full realism of wave phenomena. We're striving for simple approximation of basic room acoustics. So we improved it from image source techniques to ray tracing, which started giving us more flexibility in terms of dynamic geometry, and started approximating reverb effects quite well, especially for simple AR applications where realism is not the major target. Another important aspect that I've sort of went into as in the later stage of my PhD was the psychoacoustic impact of this system, because one question that arose quickly was, is there even point in spending a lot of computational resources and engineering into having some propagation online in augmented reality, which is a very difficult thing to do. And the question was, does he have any significant effects into acoustic abilities like localizing a sound source or estimating volume or characteristics of a room or separating sound sources? So we essentially performed some preliminary psychoacoustic testing in augmented reality with a prototype ray tracer that uses material recognition, and started looking into how well, or if having this engineered sound rendering system would have any effect on tasks like localization, so pinpointing the position and direction of virtual sound emitting object in an augmented reality space, or clustering. So how well can you differentiate whether sound, how well can you separate concurrent sound sources in AR space? And we found that it does indeed have significant effect. So the preliminary tests showed a reduction of error in both localization and clustering. Sadly, I only have graphs of localization here showing less overall error in sound sources that are around the near field or medium or far. In general, I've experienced quite a lot of growth in the application of sound rendering in quite a lot of domain of research, which are now intersecting even more due to the big traction of the metaverse. So a lot of future work would target even branches or sub-branches of the metaverse, and it would, I expect, in the next few years, sound rendering will be more ubiquitous and more accessible even for wearable computing. Robotics is another very busy research area that I'd like to dip my toes into, because of the increase in systems in automated and embodied audiovisual navigations that we have. So devices, even like vacuum cleaners, will start having some sort of perception of physical space that they can perceive, and start to recognize and perform tasks based on perceived sound sources and navigate the space accordingly. So there's increasing amounts of research in this area. I'm wary of the time, so try to keep it sort of high level. Thank you for listening, and